natural period. Frequency and time period are reciprocal of each other. Ship also has a natural period of roll. Okay. Now, if the applied force, externally applied force, its frequency matches the natural frequency of the body, then it does not become 1 plus 1 is equal to 2. It becomes 1 plus 1 equal to many a times. And this process is what is called as the resonance. You have heard this word in the schools also. Resonance is the phenomena of increased amplitude that occurs when the frequency of an applied periodic force is equal to or very close to the natural frequency of any system. When an oscillating force is applied at a resonating frequency of a dynamic system, the system will oscillate at a higher amplitude than when the same force is applied at non-resonant frequencies. Small periodic forces that are near a resonant frequency of the system have the ability to produce large amplitudes of oscillations in the system due to storage of vibrational energy. So we are just talking of pure science here as to what is resonance, and I'm sure we have studied this in the schools also. Accordingly, the resonance phenomena occurs in different branches of physics, like mechanical resonance, acoustic resonance, like I gave you the example of window pane shuddering, that is the example of acoustic resonance, electromagnetic resonance, etc., etc. Are you able to recall something about the resonance from the school now, guys? Little bit, yes or no? Correct?
Yes, sir.
Okay. Now, if you see this, okay, here there is a child on the swing and an elderly person. But if you reverse, if the elderly person sits and the child pushes, and if he pushes exactly at the right time, what is the right time? As the swing comes to its extremity and is about to start the return journey, look at this small clip. When is he pushing? See, he is waiting now, and now this is one frequency, and now he pushes at the same time. So the time period of the applied force or the frequency of the applied force is equal to the frequency of the swing, and therefore the amplitude of this swing is increasing. What happens if he does not wait for it to come to the extremity and start, and if he steps 2 steps ahead and again pushes, what will happen? It will disrupt the swing and reduce the amplitude. So why is the amplitude increasing even if a heavier person is sitting and lighter person pushes and manages to have the same frequency as the frequency of the swing? Then the amplitude will increase despite the push being small. That is because of the resonance or the synchronization between the two frequencies. What are those two frequencies? Frequency of the system, that is the frequency of the swing, and the frequency of the applied force. If they are in sync, then it leads to a condition called as resonance. Exactly the similar thing can be experienced in case of ships also, guys. Now, before we talk about the rolling, resonant rolling, which leads to increase in the amplitude of the roll, let's familiarize with few terms. We know that the waves are like this. What is the wavelength? Wavelength is the distance between two successive crests or two successive troughs. What is the true period? So, what is the wavelength? This distance here is wavelength, or this distance here is wavelength. The period of the wave, or the time period of the wave, is the time between two successive crests or two successive troughs as observed by a stationary observer. So if our observer is stationary and he sees one trough passing now, and if he's a stopwatch, and then he again sees when the second crest is passing him, the interval between the two successive crests or two successive troughs is the true period of the wave. What is the period of encounter of the wave? Now, guys, whatever is the true period of the wave, that gets modified if the observer is not stationary. Therefore, the encounter period, or the period of encounter of the wave, is the time that passes between two successive crests, or two successive troughs of a to a moving observer. The observer is not stationary. Okay, so we have three terms: wavelength, true period of the wave, and the period of encounter. This will represent as TW, and this, or TR, period of rolling, but TW is better, and this will represent as TE, and TR will be the period of natural period of roll of the ship. Are the three terms clear, guys? And including TR, we have already discussed in the morning. Am I clear? Yes or no? Clear, class?
हाँ जी सर.
Okay. Now, every vessel has a natural period of the roll, TR, which we did in the morning, 2 pi k under root GGM, which we said is inversely proportional to the square root of the GM and directly proportional to radius of gyration. And radius of gyration, we said, as a thumb rule, is 35% the molded breadth for a normal ship type vessel. Therefore, it is inversely proportional to the square root of GM and directly proportional to the beam of the ship, or the radius of gyration, whatever you want to say here. Synchronous rolling is caused when rolling period becomes synchronous with the period of wave encounter. That means the ship's natural period of roll, TR, becomes equal to period of encounter of the wave. When this occurs, the ship will heel over in an exceptional circumstances, be rolled further over by the wave action. So the amplitude will increase. If the vessel encounters a series of swell in such a manner that the wave period matches the natural period, rolling period, the vessel will have no time righting itself before the next wave strikes. This situation, if not corrected, can result into capsizing of the ship. It is like the swing. For example, let us say the ship goes to starboard. As she goes to starboard extremity and she is about to start returning back to upright, that time the wave hits from the starboard side. Now the ship would have returned because of its righting moment, but now that is also supplemented by the energy transferred by the wave. So the ship now returns with greater momentum because of the wave action. And now this ship does not, with greater momentum, when it comes, suppose let us say the ship had rolled 10 degrees to starboard. And as she was about to start, let us say from the starboard side, the wave hit. Now, obviously, the ship will not roll to 10 degrees on port. Now, it will roll much more than 10 degrees. Why? Because she has been given extra energy to roll by the wave that has hit. Now, as the ship goes to extreme port and comes back to starboard like the swing, she may, instead of 10 degrees last time, now she may go to 15 degrees, 18 degrees. As she is about to start again, another wave hits. That means now, what are you doing? The rolling period of the ship is matched with the encounter period of the wave. Okay, so this basically leads to resonance. And what will happen? This will increase the amplitude of the roll. And if you allow this to be unchecked, then the amplitude can keep increasing and the vessel can reach angle of flooding, and that can lead to loss of the ship. At the same time, there can be loss of cargo, there can be parting of lashings, there can be serious effects of excessive roll, and therefore it is important that we realize when synchronous or resonant rolling conditions are developing. Now, guys, before I show further, on what conditions the period of encounter will depend? Period of encounter will depend upon two things. One, the wave, and the second, ship. Which part of the wave? That means it will depend upon the direction of wave, and the wave period. It will also depend upon the ship's course and ship's speed. Now if so basically what is the condition for synchronous rolling? When you have the seas from a beam or nearly a beam or nearly a beam, and the natural period of the roll is ship is equal to the period of encounter, that leads to a synchronous condition, condition for synchronous rolling. Why? Because the resonance occurs between the ship and the wave, and this leads to increased amplitude of rolling. And if it is not checked, it can lead to the loss of the ship. The vessel encountering synchronous rolling is in danger that she may heel over beyond a point from which it cannot return to upright condition. That means she may reach the angle of vanishing stability and then she cannot return. This may end up with negative stability and eventually the vessel may capsize. Synchronous rolling can be experienced regardless of the direction of the sea, but it is most likely to happen when natural period of the rolling of the ship is short and when sailing in high beam seas or quartering seas. So if the synchronous, if resonance takes place, this can really endanger the vessel. Guys, does the resonant rolling or synchronous rolling make sense if you link it to the resonance that you studied in the schools? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now, if you realize that a condition for synchronous rolling is developing, now you see here, this is just a graphical representation. Ship goes to extreme starboard, and this time you have a wave hitting from as she's about to start her journey back. Wave hits as she starts back. You have the crest coming and hitting the starboard side. What does this do? This increases the speed at which it will return. When she reaches upright, the crest reaches in the center like this. And what happens now? Her ability to check the swing has reduced. Now she will heel to an excessive angle on the port side. Then, as she's about to start back, you again have the crest here. This is half period is of the wave is done, and half the rolling is done. And she then repeats the same thing, and that means the period of roll, natural period of the roll of the ship, has become equal to period of encounter, and the wave is from a beam or nearly a beam. Then that is an ideal condition for synchronous rolling to take place. What are the dangers associated with synchronous rolling? It can result into discomfort to the crew and passengers. It can lead to the cargo shifting, and when cargo starts shifting, it will have effect on the stability of the vessel. The cargo lashings may give way because of excessive rolling and causing damage to the cargo, in some cases structural damage to the ship as well. A vessel which has suffered engine failure, please make note, a vessel which has suffered engine failure is most vulnerable to synchronized rolling, and efforts to bring the vessel head into the wind should be made while she still has a headway. So if you are an officer on the watch in choppy seas and suddenly the engine stop, please use your helm before the ship stops to put your head into the wind. Otherwise, the wind may catch you on the beam and can really create problems for you. To reduce synchronous rolling, guys, what is the solution? You have to do away with the cause. What was the cause of synchronous rolling? The cause of the synchronous rolling was the natural period of the roll of the ship became equal to period of encounter. You have to break this You have to break this. How can you break this? Either you change TR or you change TE. Technically, we are talking technically. To change TR, what do you need to do? You studied in the morning, TR is equal to 2 pi K upon GGM. That means you can add ballast, you can remove ballast, or you can shift something so that the GM and radius of gyration get altered, causing the change in the TR value. Now you'll say, sir, it will take time. Yes, we are just talking technically what can be done. Whether that is a preferred action or not, that's a different issue. Okay. Or else you can change the TE. I just told you what does the TE depend upon. It depends upon the wave and it depends on the course. It depends on the ship. Which part of the ship? Ship's course and ship speed. Guys, you can't change the wave direction and wave period. You can't change the wave period and wave direction. That is not in your control. What you can change is your course and speed or both. So that period of encounter changes and this harmony of TR becoming equal to TE is disrupted. So normally on the ships, you would probably fall back upon changing the course and or speed because that happens instantaneously. But technically, you can change TR or TE. I agree with you that changing TE will be the most convenient option. But and when you anyway, technically, if somebody wants to change the TR, that is also technically in order. But practically, TE will be the most viable option to avoid synchronous rolling. Yes or no, beta? Am I right? Correct?
Yes, sir.
Okay. So what are the actions to avoid synchronous rolling is basically to disrupt the cause. Use the ballast, use ballast changes to alter kg so that GMT of the vessel. By doing so, the rolling period will change, making it a non-synchronous value. Change the course of the ship to effectively change the period of encounter and eliminate this condition for synchronous rolling. Alter the speed of the ship until the synchronous rolling ceases to exist. It is imperative that OOW recognizes the condition of synchronization immediately and immediately alters course or to change the period of encounter and eliminate this condition. So, guys, have you understood what is synchronous rolling? Under what circumstances does it happen? And what can be done? What will be its ill effects? And how can you prevent a condition of synchronous rolling being developed? Is it clear, beta?
Yes, sir.
And
सर
let me again repeat. So, yeah, tell me, beta.
सर आई अंडरस्टैंड कि अभी आपने बोला ना कि
Hmm,
व्हाट विल हैपन इफ वी चेंज द कोर्स ऑफ द शिप
hmm,
आई अंडरस्टैंड कंप्लीटली बट
hmm.
मतलब इज देयर अ प्रेफरेबल साइड आई अंडरस्टैंड दैट इधर भी मोड़ेंगे तो इट विल ब्रेक द टी आर इक्वल्स टू टी वाला
Yes, yes.
सिचुएशन
So, yes, correct. The moment you will change the course, whichever way, whether you alter to port or starboard, your the change in course is going to change that period of encounter, right? TE will be changed. Correct, beta?
is there a preferable side like into the
No,
wind
no, no. This
or
is not. This is not ROR that there is a preferable side. But during the voyage, if you have a certain preference, like one side you may have a hazard or a coast has a hazardous zone, on the other side you may have clear waters, so maybe you'll prefer to alter on the clear side. So situationally there can be preferences, but as far as technicality is concerned, you could alter whichever way, right? Am I right?
right sir yes sir
Yes, suppose you have you're navigating close to the coast and you have the coast on the starboard side, or you have a shallow patch on the starboard side, then obviously you will not alter to starboard to break the resonant condition, right? Guy, then you will alter to port. But if you have sea room on both sides, then you can alter whichever way you want. Likewise, when you say alter speed, normally we decrease the speed, but the condition technically will be violated, broken even if you increase the speed. Do you understand that? Have you understood, beta? Even if you increase the speed of the ship, the resonant condition period of encounter will change, and resonant condition ship may come out of the resonant condition. But normally we do not increase the speed to avoid stresses on the hull unnecessarily in choppy seas. But if you are talking of
I
only the
understand.
science part, so likewise, speed increase, decrease, both are equally acceptable as far as logic is concerned. It's a different issue that practically you may reduce the speed. Likewise, you alter to port or alter to starboard does not make a difference as far as breaking the synchronous condition is concerned. But which side will you alter? You can always assess the situation, and if you have a preferred side to alter, please alter the preferred side, right? Correct?
Yes, sir. Thank you.
Okay. It is not better ROR where you have to say alter to port or alter to starboard. You are basically trying to change the TE. TE will change whether you alter to port or starboard. TE will change whether you increase speed or decrease speed. TE will change in both the case or in all the four cases. Now we come to parametric rolling, guys. Now just remember in synchronous rolling, like the swing, you were being imparted energy by an external force, external entity. What was the external entity in that? The wave was the external entity which was transferring energy to basically increase your amplitude. Now, beta, every time it is not necessary that the external energy is required. Okay. Do you remember? Do you remember in this rolling test? One of the methods to induce rolling was what? Rhythmically lifting and lowering the weights. Yes or no? Correct, beta? Away from the center line. Do you remember that? Rhythmically
Yes, sir.
lifting and lowering the weights.
Anji.
Now, what,
Yeah.
what was it doing? What was it doing? It was not imparting any energy. It was changing the GM of the ship. You're trying to induce list rolling by changing the inherent parameters. So, what is parametric rolling? A parametric rolling or parametric oscillation is again a physics term. Now, see, guys, what happens if in this case? If there is nobody to push the swing, can you increase the amplitude of oscillation of swing in the park? Yes or no? Can you?
No.
You can't alone? You've never been on a swing alone when you
Can, sir.
can.
Have to push ourselves.
Yes, sir.
Yes. What do? You pump the swing. Look at this video when it comes. You see 1, 2, 1, 2. In one oscillation, he's pumping it twice. Can you see it? Yes or no?
Yes, sir.
Correct, guys?
Yes, sir.
Is there anybody pushing from outside? No. What is this guy doing? He's pumping the swing by himself. He's altering the inherent parameters of the swing, because the swing and the person on the swing is one system. So by pumping it, what is he doing? He's changing the inherent or internal characteristics of the swing, which are leading to increase in the amplitude without any external push being given. A parametric oscillator, it's again a physics concept, guys. A parametric oscillator is driven harmonic oscillator in which oscillations are driven by varying some parameter of the system at some frequency, typically different from the natural frequency of the oscillator. In this case, you see how many times did the person pump in one oscillation? He pumped twice. So the parameters were being changed twice in one oscillation. So typically it is different from the natural frequency of the oscillator. Example, a child pumping a playground swing by periodically standing and squatting to increase the size of the swing's oscillation. Now, something like this also happens to ships. It was always happening, but it was not making a very noticeable difference in the earlier times. These days, this thing has started showing noticeably in which type of ships, especially the new generation container ships. What is so special about these new generation container ships? These container ships have a fine bow. Why? Because they want to move at a very fast speed and they want to reduce the water resistance. And then they have a huge flare upwards. Why? Because they want a broad deck on which containers can be stored. So earlier also ships had flare, but that flare was not so much as today we have in the container ships. Okay, so it is this basically thing that a narrow bow and a flare, huge flare, or at the stern suddenly the body becoming fully on the stern. These things are leading to the parametric rolling. Now you will first most of the books you'll find that this changes makes the ship stiff and tender, stiff and tender. How does it make it stiff and tender? You'll understand because you have done moment of inertia and its applications only few days back. See guys, so what is parametric resonance before I show you how it is changing? Parametric resonance is the phenomena of resonance when excitation is caused not by an external push, but excitation is caused by changing key parameters affecting the oscillations. And in case of the ships, the key parameter is the GM. This effect is different from regular resonance because it exhibits varying stability conditions. Parametric resonance takes place when external excitation frequency equals twice the natural frequency of the system. We saw the person pumping the swing twice in one oscillation. Now let us understand how the stability is altered. Now guys, let us see this ship. Though I don't see much flare here, but I could find this as one of the ships. Let us say it has excessive flare, okay? Let us say it has excessive flare. If it has excessive flares, let's visualize its cross-sectional area. This is the calm sea water line, let us say. Let us visualize the water plane cross-sectional area here. If you cut the ship here and see what is the cross-sectional area, what will you notice? You will notice that at the lower end, the bow is very narrow and then it flares like this towards the deck. Do you agree with me that this represents the cross-sectional area at station A? Yes or no, beta? Has everybody understood?
Yes, sir.
Right? In the middle part, there is hardly any flare. It's parallel body. So the cross-sectional area would be somewhat like this at station B. Am I right, guys? Correct?
Yes, sir.
And the cross-sectional area in the after part will again have flare something like this. Now, because of this excessive flare, what happens? Now, suppose the vessel encounters a wave from right ahead or nearly ahead. And let us say, so we are saying wave is from now right ahead or nearly ahead. And wavelength is equal to, let us say, length of the ship in this case. Guys, if I visualize the water plane area in the calm sea condition, this yellow line is the still water line, then what will happen? This is the width of the water plane here. This is the width of the water plane here. And this is the width of the water plane here at the cross-sectional areas. And this gives me this water plane area. Okay. This is the water plane area in the calm sea conditions as at yellow water line. Now suppose the vessel encounters wave from right ahead, and let us say the wavelength is equal to the length of the ship. Okay, and you have this condition. In this condition, what is there? You have crest midships and you have trough at the two ends. Then you see the red line, the wave condition beta, where you have the crest midships And since the wavelength is equal to the length of the ship, you will have trough at the ends. Am I right, guys? Yes or no? Correct, beta?
Yes, sir.
Now, because of the excessive flare, what has happened? At station A, the water plane, breadth of the water plane area is reduced because of the flare. At station B, it does not change much because it is parallel body. It does not increase. At C, it is again reduced. So whereas the water plane area at the ends is reduced, water plane area in the middle part remains almost the same. So in the wave condition, the water plane of the ship will become somewhat like this. Do you agree with me? In the wave condition, this is the wave condition water plane, and this is the still water, right, guys? Yes or no?
Yes. Yes.
And guys, what is BMT? BMT is I of the water plane about center line divided by volume of buoyancy. So if I draw the center line here, which BM will be greater for the red water plane or yellow water plane? Tell me.
Yellow.
Yellow. So that means my BM in the wave condition is reduced. If my BM in the wave condition is reduced, my KM is reduced. If my Km is reduced, my Gm is reduced. So in this wave condition where you have the crest midships and trough at the ends, the GM is the stability of the ship is reduced. The stability is diminished. Has everybody understood? Because you might have read in the books or somewhere else
Yes.
that stability alternately increases, decreases. But how does it increase and decrease? It's because of change of the water plane area. Understood, class?
Yes, sir.
Okay. So in this condition, the stability is diminished. After some time, what will happen? This crest will move to the ends, and you will have a trough midships. You will have this condition. This condition, the down one, right, guys? Better mute yourself, please. Samuel, mute yourself, better, please. Now, what will happen, guys? The area at the ends will increase. Water plane area at the ends will increase. Water plane area in the midship region does not change much. And I'm sure you'll agree, if in upper diagram the stability is diminished, then in the lower diagram the stability will be enhanced. Yes or no? Correct? Correct, beta?
Yes.
Okay. Now what happens is this increased stability or decreased stability periodically. So stability is alternately enhanced, diminished, enhanced, diminished, enhanced, diminished. Now, if this alteration of stability, which is not being done by any other reason but because of the wave action, wave is not giving you any energy to roll. But what wave is doing is wave is changing your stability. And if the frequency at which this stability changes happens to match the rolling period of the vessel, then what will happen? The vessel will again reach a condition of resonance, but we don't call that as resonant rolling. Why? Because in resonant rolling, there has to be an applied force.
Experiment.
Correct. Here, the resonance has taken place, but we don't call it as resonant frequency. What is this doing? It is changing the internal stability parameters of the ship, and it leads to parametric rolling. So yes, there is a resonance, but that rolling is not called resonant rolling because it is here the applied force is not involved. There is a wave which is there. Wave is altering the internal parameters of the vessel. So how above changes the stability? Let me just show you more. I have done a lot of it actually with you. Let us say the vessel is in upright condition like this, and this is her GZ curve in the static in calm seas, static GZ curve. Okay. Now let us say still water GZ curve. Okay. Now let us say the vessel rolls to starboard by itself. Now, what will happen? What will make the vessel to roll? Some work has to be done, whether wave does the work or wind does the work. She inclines on one side. The energy gets stored into it. And what is the representation of that energy? It is the area under the GZ curve. So if the vessel has now, let us say, gone to this angle, whatever it is, in the still water, then this area 1 represents the dynamical stability or the energy stored in the vessel. And if nothing else changes, this area, the dynamical stability corresponding to area 1, will be responsible for bringing the vessel back to upright. But let us say at this particular moment, when the ship has to come back, let us say the ship becomes her stability is amplified. Stability amplified means GZ curve is amplified. So at this stage, the GZ curve is amplified. So the vessel is lying at theta 1 angle only. But what has happened? The GZ curve is amplified. If GZ curve is amplified, the area under the GZ curve like this is increased. So instead of area 1, which would have been responsible for bringing the vessel back to upright, now it is area 2, which is responsible for bringing the vessel back to upright. And naturally, area 2 is greater, so the vessel will come back to upright with more rapidly because of the enhanced stability as she starts her journey back. Is it understood, or anybody has any question to ask? Let me clear it and show it again. Does anybody have any questions, guys? Please let me know. That how this enhanced stability increases the momentum with which the vessel will come back. Yes or no, beta? Correct? Correct, guys?
Correct.
Now, as the vessel becomes upright, she has a lot of momentum because this area was responsible for bringing it back. She's coming with increased momentum. And as she becomes upright, she becomes tender. Her stability is diminished. What happens? Her stability is diminished means now when she comes here, the stability is diminished. This is the diminished stability curve. So what would check the vessel's roll to the other side, port side? Let us say if this is port and this is starboard. What should now check the vessel's roll to the port side? It is the GZ curve, but now the GZ curve is not even the still water, it is further reduced. So that means because of the diminished stability, whatever momentum she was coming from starboard side, increased momentum she was coming from starboard side, now there is her ability to check that swing is reduced. That means, let us say the vessel was heeled to 8 degrees here. If it was calm seas, then this area would correspond to the dynamical stability which will bring her back. But that is now enhanced because of this area 2. So at 8 degrees, she comes back more rapidly than what she would have done in calm seas. And now as she becomes upright, though she is coming with greater momentum, now the stability is diminished. So that means now what will happen? The swing that the vessel has, the vessel has reduced capability to check that swing. So that means the vessel will now not stop at 8 degrees on port side. It will go well beyond 8 degrees, maybe 15 degrees, maybe 12 degrees, maybe 17 degrees. It will go well beyond 8 degrees on the other side. Why? Because of this diminished stability in the upright condition. Now, as she reaches the extreme port now if she started at 8, maybe this is 15 degrees. Now, as she starts back from here, this is the calm sea condition. As she starts back from here, she's gone to theta 2. Theta 2, I'm saying, is 15 degrees, for example. I'm taking theta 1 as 8 degrees in my example. As she starts back, the stability is again amplified or increased. What will happen? The curve is again amplified. So up to theta 2, the area has further increased. So from 15 degrees, if there was no wave action, vessel, this area would have been responsible for bringing her back. But now this area has further increased. So that means now she comes back with more rapidly than what it should have. Now she comes with greater momentum, and as she comes to upright, the vessel again GM is reduced or the stability is reduced. That means her ability to check the swing from 15 degrees with this enhanced momentum is again reduced. And what will happen now? She'll continue going to starboard side because of the reduced ability to check the swing. And instead of 15 degrees, maybe she goes to 25 degrees, maybe she goes to 27 degrees before she stops. As she's about to start back, again, you have the same nuisance. That stability is increased. That means now from 27 degrees, she comes much more rapidly. And when she becomes upright, again, the stability is diminished. Have you understood what is happening? So the amplitude of the roll is progressively increasing, and it increases at a very, very fast speed. And this leads to increased rolling of the vessel. And what is responsible for this increased rolling? What is responsible for this increased rolling is the fact that the stability of the vessel is alternately increased and diminished or increased and diminished. And if this frequency matches with the rolling of the vessel, then this is what leads to parametric rolling. Anybody has any questions? Let me know, guys. I'll be happy to answer. Does it make sense, guys? Parametric rolling now?
Yes, sir.
See, you will not be doing all this in the paper, but once you are convinced what it is, once from within you feel that you know what parametric rolling is, then you'll be able to answer the question. Guys, in some cases, you may also hear the word symmetric parametric roll. It is the same, so don't get confused. Symmetric parametric roll, it's the same thing, because the symmetry of the vessel is basically affected because of the altered stability. So if this word is there, don't worry, you keep writing parametric rolling only. Okay, sometimes I've seen this word also in the question paper, so it should not confuse you.
Excuse me, sir.
Yeah, tell me better. Yeah.
Sir, in the beginning of discussion, you mentioned that it is mostly experienced on the container vessel, but it is experienced.
It is experienced on it is experienced on the ships which have high degree of flare at the ends, right?
Yes, sir.
Yeah, correct. Because then the area change will be much more, na beta, with the waves. You see, beta. Let me just create this space here. See, beta. One is you have very less flare. One is like this. Okay, and other is like this.
Yes, sir.
Right. Now, if this is still water line, and now here you have, let us say, the crest here. So what will happen? Even if the crest is there at the bow, the area does not increase much in this case where the flare is less. But in this case, the area will increase much more, right, beta? Correct?
Yes, sir, correct.
So the area change because of the wave and crest will be water plane area. Which area? Water plane area. The change in the water plane area width happens much more if the flare is very high, right? Flare has always been there in all the ships from past, but that time the flare was not much. So that did not alter the stability that much that it became threatening as parametric rolling. Because these container ships especially have a high degree of flare, that has led to this nuisance of parametric rolling, right, beta?
Okay, sir, understood.
Okay. Anybody who's a container person here?
Yes, sir.
Anybody?
Yes,
Who's
sir.
that? Who's that?
Siddharth.
Sorry?
Siddharth.
Siddharth, what size of container ships have you sailed upon?
400 meters long.
Okay, 400. So now you must have experienced parametric rolling, or you would have taken some precautions to avoid parametric rolling. Since whatever I am sharing, I did not sail on such big ships, honestly, like container ships. I was a tanker. I started with Scindias and switched to tankers then. Would you like to share any first-hand information or anything you want to add to what I said for the benefit of everybody?
Yes, we used to experience this parametric rolling, and then when the weather used to be choppy, or if it is not favorable, then the master used to come and advise to keep a lookout so that if this situation is not generated in the first place. And then we had to follow this. There was a checklist for this where we have to check the wave, all those criterias, and then call him.
Okay. Mhm. Okay. So basically, no, but what was the flare? Your bow, your two ends would have had huge flare, right? Am I right?
Yes, correct. This long ships used to be it looks the same way you drawn in the second to explain here in the bottom.
Okay. Okay. So basically, Akshay, the root cause is because of the flare with in crest condition and wave condition, crest and trough condition, the water plane breadths change rapidly and quite a bit. And this change in breadth will change the BM, and BM leads to change in GM. So that basically alternates the stability. It becomes more, it becomes less, it becomes more, it becomes less. Right, guys? Clear?
Yes,
You
sir.
don't have to write
Yes,
all
sir.
this that I'm showing here. This I'm just to doing to connect what you already know. And once you know why stability is changing, then there will be inherent confidence in you to explain what you're talking. And especially in orals, you'll be able to talk with more conviction. That is the purpose.
Yes, sir. Can you show the second slide, sir, where you just written parametric rolling definition something?
This is the first one. This is the first one, bete. Okay, this is pure physics. This has nothing to do with the ship.
No, sir, second one.
Okay, this one.
Yes, sir. Finish, sir.
Okay. Okay. Then this was the third one where I started explaining to you why the stability is enhanced and diminished. Okay, this is what we have discussed. Now we come to what you will write basically. Okay, so basically that is the thing. Parametric roll motions with large and dangerous roll amplitudes in waves are due to variation of stability between the position of the wave crest and position of the wave trough. This is what I have just explained to you guys. Now you know what this line means. Parametric rolling occurs when the pitching period is the period of wave encounter. Why? Because as the wave, whatever period the wave encounters from ahead or nearly ahead, the pitching period will be same. So the pitching period is either equal to the rolling period, that means TE is equal to TR, because TE is equal to TP, pitching period, right? Or TE is equal to half the rolling period. In both these conditions, parametric rolling situation can develop. Large roll angles may occur quickly in head or stern seas or nearly head or stern seas. The roll angle may increase from a few degrees to over 30 degrees only in few cycles. It does not give you much time. Guys, resonant rolling is not that dangerous as parametric rolling. Okay, because this is very random rolling. Parametric rolling is very, very random rolling. Okay, this is the slide, Sahil, for you. Okay.
Okay, sir. Done.
It is caused due to combination of various factors such as low initial stability of the ship, large flare around the waterline. If around the waterline you have large flare, the water plane area will change immensely, leading to the change in stability. Wavelength as long as ship's length. So IMO says it is up to 1.5 times the length. Anyway, sufficiently large wave amplitudes, guys. Wave amplitude. What is the wave amplitude? This is the wave. The height between the crest and the trough. This is the amplitude, right? So if this is high, then the area changes will be much more. So if the wave amplitudes are high, that will be creating a situation for parametric roll. Period of encounter equal to or half the rolling period we just said a while back. Low hydrodynamic rolling damping. That means the ship has the shape of the ship is such that it does not have inherent, the hull does not have the inherent damping effect on the rolling. Parametric rolling is produced by the pitching motion on vessels which have large fine bow together with very wide and flat stern, like large container ships which have a large flare forward and flat after part of the ship. Parametric rolling is more when a vessel is operating in heavy sea conditions. Such conditions can generate extremely high loads on the lashings and containers. It can even exceed the breaking load of the container lashings. As a result, the cargo and the vessel could be damaged and containers could be lost overboard. Okay. Parametric rolling causes heavy stresses in the ship structure. Parametric rolling causes heavy stresses in the ship structure, especially the ends. It also causes variation in the load on the ship's main engine because the propeller is sometimes going deep into water, sometimes coming up. So you have the propeller racing also, which takes place. If not tackled quickly, it can also result in the capsizing of the ship. As the stern dips into the wave, it produces a rolling action. The rolling action is different at the stern and those at the bow. That means on one side, the stress is acting on one direction and in the others, it is acting on the other direction. I have a video on torsional stresses if you would like to see that. So the rolling action is different at stern and then those at the bow, which causes the twisting along the ships, leading to extra rolling motion and torsional stresses. IMO suggests that parametric rolling is dangerous when wavelength is 1 to 1.5 times the length of the ship. So anything between this, it is the parametric rolling. Of course, it is for the ships where parametric rolling can occur, not for every ship, right? If you don't have excessive flares, then it will not happen. Ships which have high GM will have shorter period of roll and unlikely to have parametric rolling. So that means if you have initially, we said earlier also, if initially the ship had low initial stability, they are more prone to parametric rolling. Ships which have low GM will have a long rolling period and are likely to have parametric rolling in head or stern seas. Okay, that's this page, Sahil. Okay. To reduce parametric rolling, what actions are suggested? Again, you have to break the rhythm between what? The period of encounter or pitching period, whatever you want to call, and the period of roll. You have to break their friendship. Now, period of encounter or pitching period can be changed. You can't change the wave direction and wave height. What you can change is the course and speed of the vessel. TR, rolling period of the ship, can be changed by changing the K and the GM. Obviously, the most viable option will be course and speed because especially in parametric rolling, you don't have time to really waste in taking corrective action. So, but technically, what you're seeing on the screen is a technical aspect. Yes, if you can change quickly the TR, then also the parametric rolling can be avoided. Anti-rolling stability tanks to be provided to transfer water across the ship. A quick response time is vital to counteract this rolling. Siddharth, what did you have? Anti-rolling tanks, or what did you have to as a damping
We had
mechanism?
anti-rolling tanks.
You had anti-rolling tanks, okay.
Ships before that, we used to have this fin stabilizers.
Yeah, the next is hydraulic fin stabilizers could also be an alternative, right? So any of these two, they are all basically anti-rolling devices, right? Rolling
Yes,
damping
yes.
devices. Slow down and alter the course, alter to a more favorable course to ease the vessel's motion by breaking resonance between rolling period and period of wave encounter. So any of these things you can do, guys, but of course, the most viable will be course and speed, undoubtedly. So guys, I hope now you'll be able to write something about synchronous rolling and parametric rolling if it is asked in theory. Am I right?
Yes, sir.
Yes, sir.
Anything you want to see before I close this? Tell me. Okay. Discard. Now we go to the last part of it. What is the last part of it? Is the deterministic and probabilistic method of stability. Guys, till 2009, we were following this method which is called deterministic method. And in 2009, chapter 2.1 of SOLAS was amended to introduce the probabilistic method. Okay. But you see, what has happened is different conventions of the IMO came at different times. You had SOLAS, you had load line, you had MARPOL, you had IGC, you have different conventions coming as the need arose. Now, guys, all these conventions have damage stability criteria. Now, some are applicable to all types of ships. Basically, they are applicable to ships which are covered by those conventions. For example, damage stability criteria in MARPOL will be applicable only to tankers. Damage stability criteria in SOLAS will apply to all ships. So it depends what we are talking about. So what happens is that these conventions came at different times and they have different requirements slightly. So what has SOLAS done? Though the SOLAS chapter 2.1 was amended, but SOLAS naturally, suddenly you can't expect everybody to start doing that line. So what has SOLAS said is that any ship which is already following the damage stability criteria under any of the existing IMO instruments, that means under IMO conventions, can continue doing so. So today what has happened is the tankers are still following the deterministic method. So there is nothing wrong in it. Okay, but deterministic method is more or less now going to be phased out as the time allows. But today, since both are there, we'll just run through both of them. Now, basically, whether it is deterministic or probabilistic, it doesn't matter. In 2009, comprehensive amendments to SOLAS Chapter 2.1 were made in relation to subdivision and damage stability requirements in order to harmonize the provisions for cargo and passenger ships. The revision of SOLAS Chapter 2.1 was to incorporate probabilistic method of determining damage stability, which is different from previously used deterministic method. Although both these methods are different, the objective of both the methods is the same. What is the objective? To ensure the safety of the vessel in case the hull is breached. So what is the objective? Is that ships shall be efficiently subdivided as is possible, having regard to the nature of service. Nature of service means whether it's a passenger ship, it's a cargo ship, what type of ship is it, for which they are intended. The degree of subdivision shall vary with the subdivision length of the vessel. More you have studied in the bulkheads in phase 1. Longer the ship, more will be the number of bulkheads required. and with the service, nature of service, in such a manner that the highest degree of subdivision corresponds to the ships of greatest subdivision length. So greater the ship length, more will be the subdivision. And based on type, if two ships have the same length, passenger ships will have greater degree of subdivision compared to cargo ships, because passenger ships have more lives on board. The damage control plan and damage control booklet, which is required by SOLAS Regulation 2, 1/19, are intended to provide ships officers with clear information on the ship's watertight subdivision and equipment related to maintaining the boundaries and effectiveness of the subdivision, so that in the event of damage to the ships causing flooding, proper precautions can be taken to prevent progressive flooding through openings therein, and effective action can be taken quickly to mitigate and, where possible, recover the ship's lost ship stability. You have a damage stability booklet and you have a damage stability control plan, which will basically guide you what action to take in case of any damage to the hull of the ship. So guys, the objective of both the methods is same. Deterministic method was not bad. It has served the industry for long. So there's absolutely nothing wrong with it. Only thing is, deterministic method was little too rigid because it did not apply, it did not factor many things. So to factor in the comprehensive environment of the ships, this probabilistic method was introduced. What is this deterministic concept? The deterministic regulations were such that based on the assumed damage scenario, like, and in that what used to happen, depending on the length of the type and the nature of service, a ship could be one compartment ship or a group of compartment ship, one compartment ship, two compartment ship, three compartment ship. What does it mean? That means depending on which rules were applicable to that type of ship, they would say, okay, it's a one compartment ship, means this ship should be able to survive damage to any single compartment, right? If it was a two compartment ship, what it meant was that the ship should be able to survive the damage to two adjacent compartments. If it was a three compartment ship, the ship should be able to survive damage to three adjacent compartments, right? So the deterministic regulations were such that based on the assumed damage scenario, according to the ship's factor of subdivision, the maximum permissible length of the compartment obtained was calculated, and that was what was ensured. So in under deterministic method, what did they do? Depending on the type of ship, whether it was one compartment, two compartment, three compartment, depending on the length of the ship and subdivision, you determined what is the maximum length a compartment can have, and you made sure that that maximum length of the compartment is not exceeded. You determined it, and end of the story. Now, to understand deterministic method, there are few terms which you must understand, and there were many more which are there in the older questions, but now in present SOLAS, those terms do not exist. And even these many terms don't exist in today's SOLAS because deterministic method is no more found in the SOLAS, okay? Bulkhead deck, margin line, maximum floodable length, allowable or permissible floodable length, and factor of subdivision. These are the five terms in today's context that if we know, then probably we can appreciate the deterministic method better. What is a bulkhead deck, guys? Bulkhead deck is nothing but a deck to which the watertight bulkheads are carried. Which watertight bulkheads? Here we mean the transverse watertight bulkheads. So there can be, what is a margin line? Margin line is an imaginary line drawn on the side of the ship. Imaginary line, not physically drawn, where? On the side of the ship at a distance of not less than, it is not equal to, not less than 76 mm below the bulkhead deck. Okay, we'll come to margin line, why it is 76 and all that. You see, in this particular case, all these bulkheads are carried to the same deck. So this is the bulkhead deck. It is continuous from one end of the ship to the other end of the ship. In some other ships, you may have some bulkheads carried to one deck and other bulkheads carried to the other deck, like this one. You have some bulkheads carried to this deck and other bulkheads carried to this deck. So that means in some parts you had deck 1 acting as the bulkhead deck, and somewhere you had bulkhead deck 2 acting as the bulkhead deck. Of course, there were certain other compliances to be done for length of these compartments. We'll not go into that details. In the second case, the margin line will be drawn with respect to each of the respective bulkhead decks. So margin line in this part is drawn with respect to this bulkhead deck. Here it is with respect to deck 2, and here again with respect to deck 1. So guys, the bulkhead deck is the deck to which the watertight bulkheads are carried. And margin line is not physically drawn, it's an imaginary line drawn at a distance of not less than 76 mm below the bulkhead deck. Now, why are we talking about this margin line? Guys, your ship's watertight chamber is made of keel at the bottom, ship sides on the sides, and the deck on top, bulkhead deck. So actually, the ship will remain afloat till the bulkhead deck goes below the water. Okay. Now, would you like your ship to immerse right up to the bulkhead deck? No. You would like to, like you have a breaking load of a wire. Do you want to put that much of load on the wire that the up to the breaking load? No. What do? You have a safety factor and you come to SWL so that you don't exceed the safe working load. Likewise, technically, you can immerse up to the bulkhead deck. But would you like to immerse your vessel right up to the extreme? No. You want to have a safety margin. This safety margin should not be less than 3 inches. And 3 inches, when converted into centimeters and millimeter, it translates to 76 mm. So they wanted a minimum safety margin of 3 inches. Minimum. If a owner wants to have 10 inches of safety margin, fantastic, no problem. But they did not want any margin less than 3 inches, which is now 76 mm. To mark that safety margin line, the safety limit, this margin line was introduced. So margin line is the line which you would not like to immerse in water. So that leaves you with 3 inches of safety margin up to the bulkhead deck. Is the concept of margin line clear, guys? What is a margin line and why it is required to be below the bulkhead deck, and why not less than 76? Because they don't want a safety margin of less than 3 inches or 76 mm. Clear, guys?
Yes, sir.
Yes, sir.
Now, I'll just put off my headphone because I'll play this video. I'll just unshare the screen and reshare with the system sound in. Give me a minute. Okay, share with system sound in. Okay, guys. Let me play this video here. Please watch it. Why is it not going full screen?
Hello, my name is Laura Alford. This video is going to be about subdivision and floodable length. So subdivision and floodable length follow along with what we were talking about with the flooding of a ship. So your ship has become damaged, it has flooded. What are you going to do about it? Obviously, we would like to try and restrict the flooding effects as much as possible. We can use watertight bulkheads.
1 second, guys. Let me just see why it's not coming the full screen. Let me just.
bulkheads to divide up the spaces in the ship and contain the flooding.
One second. Okay. Guys, can you hear? Can you now hear the sound? Video sound?
Yes, sir.
Okay.
Hello, my name is Laura Alford. This video is going to be about subdivision and floodable length. So subdivision and floodable length follow along with what we were talking about with the flooding of a ship. So your ship has become damaged, it has flooded. What are you going to do about it? Obviously, we would like to try and restrict the flooding effects as much as possible. We can use watertight bulkheads to divide up the spaces in the ship and contain the flooding to the minimum possible number of spaces. One way to calculate how many watertight spaces you need to have is by calculating the floodable length of the ship. So first, some terminology. Here's a little cross-section of a ship. You have watertight bulkheads, which are just walls that are watertight, right? No water can get through. These lead up to a bulkhead deck, which is also watertight. You might recall that this was the Titanic's problem. It had the watertight bulkheads, but not the bulkhead deck, so water was able to spill from one space into another. We no longer have that problem. If a ship is damaged, water will come in, it will flood, but flooding is restricted because of the watertight bulkheads and the bulkhead deck. But the question is, how many watertight bulkheads do you need? We can appreciate that probably more of them is good, but then it makes it hard and expensive to make the ship. Sometimes you need to have larger spaces because of cargo holds. So you need to figure out exactly how many you need to have. One way to do this is to use the floodable length. So floodable length is kind of a weird concept. So I've got some pictures here that hopefully will help make sense. In general, the floodable length is the length of the ship that when it's flooded will cause the ship to sink and trim such that the margin line is immersed in the water. The margin line is an imaginary line. It is a minimum of 3 inches below the bulkhead deck. And what it means is it's like a bulkhead deck with a factor of safety put on top of it. So if the margin line is submerged, it says that's the maximum amount of flooding that the ship can handle before it sinks. A couple of assumptions. The flooding is assumed to be beam to beam. That means it goes from one side of the ship all the way to the other. And also that floodable length is centered at the middle part of the entire floodable length. So like at point A here. Okay. You can do this analysis from one end of the ship all the way down to the other. So here I've got something started at the bow of the ship, right? The ship has flooded such that the margin line has been immersed. And for this illustration, I'm not including the effects of trim, though when you're calculating it, you do. I just don't have it in with these cartoons because it'll get a little complicated. So what you do is you have the floodable length. It is so much, and that will cause the margin line, like I said, to be immersed. You can take that floodable length and also plot it vertically. It's the same scale, and put that little dot there. Right here. Okay, you can take this and then do the same thing all the way down the entire length of the ship. And you can see that it changes because the geometry of the ship changes. So you plot it along all the way down here and say, voila. If you connect the dots, you get the floodable length curve. And you can see that there are some regions of some shorter floodable lengths. This is because the ship trims, right? So if there's a bunch of flooding up in the bow, the ship will trim, bow down, and that will immerse the margin line faster. Similar with the stern, right? If the stern starts to dip down, that margin line is going to get immersed much sooner. In the middle, because the ship will sink parallel, it will sink evenly, the floodable lengths are actually a little bit higher. And then relatively speaking, there's longer floodable lengths at either end. This is because the bow and the stern of the ship are narrower than the middle part of the ship, the mid-body. It really goes back to a calculation involving volume, right? So if you have length times width, well, if your width is much less, then you can get away with a longer length. Okay, so the floodable length curve. Remember that the floodable lengths are centered around the midpoints of the flooding, okay, right here. you can take that then and you can draw these little triangles here, and these will come into play in a little bit. But generally speaking, then you draw floodable lengths, connect them with triangles here. And then this, once you clean it all up, this is the floodable length for a given permeability. And this is the traditional way that you would see a floodable length curve with these diagonal lines, then how it changes, and then going back down to the bow and the stern there. You can take that floodable length and you can do it for different permeabilities for those spaces. And you can either do it for, as I've shown here, where it's one permeability for going down the whole length of the ship. You can even do it piecemeal, right? Like if you know these different spaces have permeability of 0.9 or 0.8 or 0.7, you can do it in little bits and pieces. I've seen it both ways. So what is the point of all of that? You can use the floodable length to test your bulkhead locations. This is what you do. So you take a ship, you've chosen some bulkhead locations, you want to evaluate them to make sure that it's going to be sufficient to have contained flooding for your ship. All right. So you take the ship, overlay the floodable length curve. So remember, the floodable length curve is the allowable flooding that can happen for the ship before it sinks for a given permeability. You take that, draw these little floodable length triangles for each one of these compartments. And this is kind of a confusing diagram at first. Look at it a few times, come back and watch the video again if you need to. It will start to make sense. But what it really is it's floodable.
Guys, this diagram is not confusing. If you go back to the previous diagram, just the one before it where the triangles were not there, just next to it, let me just.
You can get away with a longer length.
Okay.
Okay.
Now so this one, guy. Okay, now where the bulkheads come.
The floodable length curve. Remember that the floodable lengths are centered around the midpoints of the flooding. Okay, right here. You can take that then and you can draw these little triangles here, and these will come into play in a little bit. But generally speaking, then you draw floodable lengths, connect them with triangles here. And then this, once you clean it all up, this is the floodable length for a given permeability. And this is the traditional way that you would see a floodable length curve with these diagonal lines, then how it changes, and then going back down to the bow and the stern there. You can take that floodable length and you can do it for different permeabilities for those spaces. And you can either do it for, as I've shown here, where it's the spaces have permeability of 0.9. So what is the point of all of that? This is what you do. So you take a ship, you take the ship,
okay,
overlay.
This is where we were. This is where we were. Now, the triangles that she was making, now floodable length, can you hear me? Floodable length curve is superimposed on the ship, right, guys?
Yes.
And then she's testing if the bulkheads location I hope they are not, spacing is not more than what is required. So now what is done? At the base of each bulkhead here.
Floodable length curve. So remember, the floodable length curve is the allowable flooding that can happen.
1 second, guys, 1 second. Okay, I'll not be able to show it here. Can you see the pointer on the screen, guys? Can you see the cursor?
Yes, sir.
Okay, so now at the base of each of these bulkheads, she has drawn lines parallel to this one, like this one, 1, 2, 3, 4, which will come in the next one. And then similarly, from the base of each bulkhead, she has drawn this line parallel to this, like this 1, 2, 3. And this is what she was trying to explain when she said it is a little confusing diagram. You see, parallel to this, she has drawn these lines. And then parallel to this, she has drawn these lines. And this is how these triangles are made. Understood, guys? Okay, so where she said that
each one of these compartments. And this is kind of a confusing diagram at first. Look at it a few times, come back and watch the video again if you need to. It will start to make sense. But what it really is it's floodable lengths for each of these compartments. And it's not continuous, sort of like the original one was, right? Because you've restricted the flooding because of the bulkheads that you placed in there. So you draw the triangles for each compartment and each pair of compartments. And then you can trace over them. You can trace the actual floodable lengths for the one compartment flooding, that's the lower teal line. And then you can trace the actual floodable lengths for the two compartment flooding, that's the purple line. All right. You compare.
Now you see, guys, this light greenish one, you see these vertices of these triangles, they are basically the lines for one compartment each. right? When you take this
Yes.
purple vertices, they are from
From
two compartments. This line is from here, and this line is from the second compartment, and then you are getting a two compartment vertices here. These are single compartment vertices, and these purple ones are two compartment vertices.
The actual floodable lengths, those highlighted lines, to the allowable floodable lengths, which is the red line, okay? For this case, because the purple line is completely underneath the red line, it means that this is a two-compartment ship. It means that any single bulkhead can be damaged and be taken out, and the ship will not sink. That's a good thing. Here's another example. Same ship, but now we have fewer bulkheads, so we have larger compartments. We'll overlay it with its floodable length curve here. This is different permeability. We take it, again, draw the floodable length triangles for each compartment and pair of compartments. But now we have less bulkheads, we have larger spaces, and so the triangles are correspondingly larger. We do the same thing, highlight the lines for the actual floodable lengths for the one compartment flooding and for the two compartment flooding, and we see, this part of the two compartments triangles is above the floodable length curve. The one compartment triangle is all underneath this, so that's okay, but that little part is above the allowable floodable length curve. So what it means is that if this bulkhead is damaged, these two compartments are going to flood and the ship is going to sink. So this is only one compartment ship. So you can appreciate, right, that a two-compartment ship is safer than a one-compartment ship. A three-compartment ship is probably safer than a two-compartment ship. But eventually, you could put in so many watertight bulkheads that, you know, any damage at all causes 5 of them to flood, and so it sort of defeats the purpose. So this calculation with the floodable length, and there's also a factor of subdivision, which is kind of like a safety factor, is an older way of doing it. And you can still do it, and it's actually not a bad way of just sort of checking things, right? Okay, does this make sense? But it can't capture a lot of things about ships that happen, that we know happen. So the new way that we do things is really with a probabilistic damage assessment, and this is actually fairly involved, so this will be in the next video. That we'll go through it. So, but the floodable length, it gives.
Okay. Now, whatever we have seen there will be repeated on the screen, and if you have not understood anything, please let me know. Now, what is maximum floodable length? Maximum floodable length at any point along the length of the ship is that length with the point in question as the center, which can be flooded without immersing any part of the margin line when ship has no list. That means like this, guys. Let the floodable length curve comes and then I'll explain to you. Floodable length curve, you saw this floodable length curve. It's a curve drawn showing maximum floodable lengths along the ship's length. The floodable length closer to the midship is larger compared to the ends of the vessel, since the flooding of the midship compartments are accompanied by parallel sinkage, and the flooding of the ends is also accompanied by change in trim. So obviously smaller compartments, if trimmed at the ends, will bring the margin line faster to the water line compared to the similar compartment midships. Thus, floodable length varies along the length of the ship, and its variation is obtained by vertically plotting the floodable length along the ship's length. The floodable length along the length of the ship is a function of permeabilities of each compartment. More the permeability of the compartment, more will be the water ingress. We already know that in case of hull breach, and as a result, lower will be the floodable length at that point. What is a floodable length curve? This is what you had seen a while back. Now, you see, if you take point P, guys, at point P, this is the floodable length, maximum floodable length. What does it mean? Half of it will be on this side, half of it will be on this side. Point P will be the center of this. So at P, this is the floodable length. You can't have a compartment greater than this at P, otherwise the bilging of that bigger compartment will lead the immersion of the margin line. So this L, which is the floodable length, will be with P as center. So if somebody says what is the maximum floodable length at P, maximum floodable length at P is L. That means if with P as center, you cannot have a compartment longer than L. If you have a compartment longer than L, then when that compartment gets bilged, then the margin line will go under the water, which is not acceptable. Is that clear, beta? Is it clear?
Yes, sir, clear.
Okay. What is allowable or permissible floodable length? Now, one is maximum. Second is how much can you have? What is the permissible on a ship? It is the floodable length allowed by multiplying the maximum floodable length with a factor of subdivision. Now we'll come back to this once we understand factor of subdivision. What is factor of subdivision? It's a number, it's a numeral that indicates the number of adjacent compartments that, if flooded, would not cause the margin line to submerge. That means if you have one compartment whose bilging the vessel can withstand, only one compartment, okay, then you would say that it has a factor of subdivision of 1. If the vessel can withstand the bilging of 2 compartments, then you'll say factor of subdivision is 0.5. That means 1 by 2. If the vessel can withstand the bilging of 3 adjacent compartments, then the factor of subdivision will be 1 by 3. That means 0.333. So it is a numeral that indicates the number of adjacent compartments that, if flooded, would not cause the margin line to submerge. That is, how many adjacent compartments bilging can a ship withstand? It is reciprocal of the number of adjacent compartments flooding that the ship can survive. For example, a factor of subdivision equal to 1 means the margin line should not submerge if only one compartment is bilged. A factor of subdivision equal to 0.5 means the margin line should not submerge when 2 adjacent compartments are bilged. Now, this factor of subdivision will decide upon what is the allowable or permissible floodable length. Let us say a ship has a maximum floodable length at one point, at any one point. Let's say maximum floodable length is 30 meters at point X. Now, if the factor of subdivision is 1, then permissible floodable length will also become 30 meters. You can have a spacing of 30 meters between the bulkheads. But if the factor of subdivision is 0.5, then your permissible floodable length will be equal to 30 into 0.5, that is 15 meters. Why? Because you want 2 adjacent compartments to be, you want the vessel to withstand bilging of 2 adjacent compartments. So obviously that will be possible only if you reduce the length of the compartments. So you'll have to divide this 30 meters of maximum floodable length into 2 compartments by placing one more bulkhead, and the maximum spacing can be only then 15 meters. Is that clear, beta? Understood?
Yes, sir.
Okay. So this is what is your basically allowable floodable length and factor of subdivision. And so under the deterministic method, what was happening? Under the deterministic method, you were determining the length, permissible length of a compartment. That's it. Now, guys, one thing you'll all agree with me that the chances of survival of a ship, they depend on reserve buoyancy. I'm taking a very simple example. The ship may be sometimes carrying full load. That means freeboard is less, the reserve buoyancy is lesser. Other times she may be in ballast, the draft may be less, the freeboard will be more, and she'll have more reserve buoyancy. Now, the deterministic method failed to take that into account. Why? Because he'll make it one time, they'll say, okay, this is the maximum floodable length, this is the permissible floodable length, and you place your bulkheads accordingly and end of the story. It does not take into the other factors. The same ship, if it has to ply in sheltered waters, that is not taken into account by the deterministic method. So deterministic method is a good method, but probably it was not bringing in flexibility into the system. It was becoming over conservative. It was becoming over conservative. Now, what then the industry pushed for was, they said, okay, deterministic method, nothing is wrong, but then it is just one-time work you do and that's it. It does not take into account many things. For example, guys, in deterministic method, whether the ship is single hull or double hull, whether the ship has single bottom or double bottom, the length still got fixed. Okay, we all know that if you have a double hull tanker, the chances of the cargo compartment getting damaged are much lesser compared to a single hull ship. Now, deterministic method will not factor that in. For it, whether it is protectively located compartment or it is not protectively located, both will be treated the same way. So therefore, deterministic method was becoming over conservative. It was good for the safety of the ship, but it was somewhere becoming over conservative. And therefore, the industry pushed for probabilistic method. What is the probabilistic concept? Under this approach, the approach is based on probability of damage and probability of survival. So it takes into two factors. What is the probability of a compartment getting damaged? And what is the probability of the vessel surviving the damage? Okay, probability of getting damage is so much, but if this damage takes place, what is the probability of survival? Both need to be taken into account as far as the current method is concerned. In this method, an attained index is a measure of ship safety after the damage or collision. I'll talk about this attained and required subdivision index later. Let's not worry about this. This I'll come later to you. Let's watch this video and then I'll come back to explaining this thing to you better.
I love winters, a season of warmth,
Can you hear
love,
the sound?
and
Video
care,
sound?
even for my skin.
Yes, sir.
Okay.
Hello, my name is Laura Alford, and this is our hydrostatics video on probabilistic damage assessment, which I promise is not nearly as ridiculous as it sounds. So, recall from one of our previous videos that we were talking about this thing called subdivision. And subdivision is just when you take the hull of your ship and you break it apart into pieces, into compartments. The reason being is that in case something happens to your ship and one of these compartments floods, you can restrict it to just that one compartment or maybe the one next to it if you actually manage to take out a bulkhead. But this means you can restrict the flooding, and then hopefully that gives your people time to get off board, off the ship onto lifeboats or onto another ship, and hopefully keep the ship upright, safe, and stable. Right. Along with this concept is this thing called floodable length. And as I mentioned before, floodable length is kind of an older way of looking at whether or not a ship is going to be able to survive a given sort of damage. And so to make the floodable length, right, you go somewhere along the length of the ship and you figure out how much on either side of that point can the ship flood and still have the ship be basically upright, safe, and stable so that you can get people off. Right, you do that all along the ship and you get this red line, right? That's the allowable floodable length for your ship. The actual floodable length that you're going to get is going to depend on where you put your bulkheads. So once you put your bulkheads in and you get your subdivision set, you need to go back and check it and make sure that all those the actual floodable lengths are underneath the allowable floodable lengths like we've talked about before here. Right. But like I said, that is sort of an older way of doing it. And eventually something happened that made us all think that maybe there's a little bit better way of going about this. What I'm talking about is this the tragedy of the Andrea Doria. Now, the Andrea Doria was a passenger liner, and she was inbound from New York City. And as she was going by Nantucket, Massachusetts, there was another passenger vessel called Stockholm. The Stockholm was heading out into the Atlantic. Andrea Doria is coming down out of the Atlantic, heading for New York. Both ships saw each other. They had this newfangled thing called marine radar that was developed in World War II, and we can see other ships and things that are far away. And we should have been able to avoid a collision, but unfortunately, marine radar was still kind of new, and I think the operators weren't quite up on how to interpret all of the results. And what happened is that instead of the ships seeing each other and one coming this way, one coming this way, and then turning to avoid each other, they kind of turned into each other, and they ended up colliding. So the Stockholm ran into the side of the Andrea Doria, gave her a severe lift, and she ended up capsizing. Okay. So this is the two different damage scenarios that we've got. The Andrea Doria, right, massive starboard damage, heavy flooding, severely listed over to the starboard side, which meant that the port lifeboats could not be lowered. Fortunately, there were many boats nearby, and there about, I think it was 51 people lost their lives, but everybody else was able to be rescued due to some very good organization and very quick response on the part of some nearby ships. The Stockholm you see here has a completely mangled bow, but managed to stay upright and afloat. So, and you look at these two things, and both these ships were okay design-wise, right? Like the Andrea Doria, she was designed to withstand 15 degrees of lift. Unfortunately, in this accident, she had 20 degrees of lift. And so the old rules they're finding it wasn't enough. And so, well, what can we do? There's got to be something better, right? Because the problem is we don't know where the damage is going to occur. We don't know, could it be here? Or it might be here. Or it might be here. It might take out two compartments, and in that ship would sink. So we just don't know. We don't know what to do. What's that? Oh, sometimes we do know. We know more. We know more than we think that we do. So, for example, for ships to survive, we know it depends on a bunch of things. And it depends on the kg, the trim, permeability of the compartments that got flooded, how many of them got flooded, what are the environmental conditions? Is it a nice, pretty day where lots of ships can see you and come to your rescue? Or is everything obscured by rain and fog? How far away is help, right? With the Andrea Doria, there was lots of boats that were nearby, and they were able to get there quickly. So all that stuff is going to factor into how your ship is going to survive. But that's really complicated. Right, that's a lot of stuff to think of, and if you're trying to compare designs, that's too much. Like, we need one thing to look at. All right, so in engineering in general, we're never going to know everything. Right, it's just there's uncertainty all around us, but we still need to take this into account so we can actually make a design that's going to work, and we've got some confidence in it, right? So probability theory is what we use to capture all of this uncertainty and still make good designs. For the ship survivability, we can do some calculations, right, on damage stability. We can figure out how does the GZ curve change when compartments get flooded, and how does that affect the kg and the trim and the depth and the draft. We can figure all that out, except that we don't know which one is going to be applicable at the time of the damage because we don't know where the damage is going to be. Right, so all of that is still kind of uncertain, and so we're going to take all of that together, and we're going to turn it into use this probabilistic damage assessment and try and lump all of that together so we can come up with one clear picture of how safe our ship is. Right? Okay, so the Safety of Life at Sea Convention first met after the Titanic sank, because the Titanic did not have enough lifeboats for all of its passengers. And so that's the first time it met. And it's met every once in a while since then, whenever something new comes about and it's okay, we need to make a big change in the rule shift for classifying vessels and ships. So their recommendation after the Andrea Doria was that we needed to use probability to evaluate the survivability of our ships. So we needed to go and figure out, how are the ships damaged? How often does that damage occur? And then given that kind of damage, what are the chances that you're going to survive it? And we got to roll all that together into one thing. All right. So to do this for your ship, you're going to make big, giant tables. We love tables, right? So the first thing is look at if the compartments flood one by one. So look at compartment 1. Figure out what is the probability that only compartment 1 is going to flood. Figure out what the probability of surviving compartment 1 being flooded. If you multiply those two together, it's P1 times S1 there. That's the probability that you will survive compartment 1 being flooded. Right? Do the same thing for compartment 2, compartment 3, compartment however many you've got. Right? Add all those together, and that's the sum of all the probabilities. So that's the probability that you will survive any one compartment being flooded. Okay? Fair enough. Do the same thing, but now look at 2 compartments. So now we've got compartment 1 and 2. So what's the probability that both of those compartments flood at the same time? And then what are the chances that you're going to survive that compartments 1 and 2 are flooded? Multiply the 2 together, and then that's the probability of surviving that particular flooding case, the compartments 1 and 2. So again, so do 1 and 2 and 2 and 3 and 3 and 4, all combinations that you've got. Add all those together, and then that's the probability of surviving any 2 compartments flooding at any given time. All right. Again, you can do the same thing for 3 compartments, 4 compartments, however detailed that you want to get, right? You just keep multiplying these all together and then adding them up. So for this case right here, it's the probability of 3 compartments flooding. Now, buried in all of this is actually a whole lot of details. There's things that you have to worry about, like, does the entire compartment flood? Does it flood all the way across the ship transversely? Does it flood all the way vertically? There's lots of other factors that are in here that I don't have the space or time to get into in this video, but it is in the rules and regulations for your ship. And then another thing just to point out is that the probability of compartment 1 and 2 flooding, or compartments 1, 2, and 3 flooding at the same time, is not the same as just adding up the probabilities of each compartment flooding on its own, right? So again, there's a whole lot of probability theory that's rolled into this that I could maybe do if we had about 6 more videos, but we don't. So just, I'll leave it at this and say that all of these tables, likely at wherever you work or whatever school you're at, somebody's probably got a version of this already. So you just can get that.
Okay, forget about it. Just leave it. No mind. Okay, now let me just come to the main thing. Okay, guys. If you have to write something about probabilistic method of damage stability, please go about like this. Let me insert a slide here. Write something and continue here then. Okay. Now, guys, if you're to write something about probabilistic method of damage stability, what will you write? You will start by saying probabilistic method introduced by amendment of SOLAS chapter 2.1 in 2009. What does this focus upon? This method focuses upon one, probability of a compartment or group of compartments getting damaged. 2, probability of vessel surviving the damage. So this is the backbone of it, surviving the damage. Okay. Now, the probability of compartment getting damaged, probability of the compartments getting damaged depends on the location of the compartment. For example, guys, tell me, is it a cargo hold number 2 or 3 more likely to get damaged, or a 4-peak tank is more likely to get damaged? Which is the probability is higher, for the peak tank or a cargo hold?
Peak tank.
4-peak.
So that means the probability of different compartments of getting damaged is different. Okay, so the probability of compartment getting damaged depends on its location. If it's protectively located, probability will reduce. If it's located in a zone which is more prone to accidents, probability will increase. Then the probability of surviving the damage, vessel surviving the damage, depends on what? It will depend on the stability, the GM of the vessel. It will depend on the trim of the vessel. It will depend on the list of the vessel. It will depend on the freeboard of the vessel. That means the draft of the ship. It will depend on the weather condition, whether sea is rough or smooth. It will depend on availability of rescue and salvage facilities. It will depend on the atmospheric conditions. Will the probability of surviving depend on all this? Yes or no, guys? Am I right?
Yes.
Do you agree with me?
Yes, sir.
Okay. What do you do then? If it is the probability of getting the compartment damaged and probability of surviving depends on many factors. So what is done? And how do you ascertain whether the vessel is meeting the requirements under the probabilistic method or not? What do you do? Under this method, under probabilistic method, required subdivision index of the vessel is calculated as per regulation 6 part B1 chapter 2.1 of SOLAS. Would you like to take the screenshot of this one quickly, guys, if you want to? Can you read it afterwards? Will it make sense to you?
Yes, sir.
Okay. Taken the screenshot?
सर
Yeah.
सर ये 5 नंबर में रिक्वायर्ड सब डिवीजन आगे क्या लिखा है वो?
Required subdivision index, INDEX index.
Okay, index
Is calculated as per regulation 6 part B1 chapter 2.1 of SOLAS, which is now coming up on the screen. Is that clear, beta? Is it okay?
Okay, sir. Okay.
Okay. Now, this capital R is calculated as per SOLAS regulation 6. Now, for ships to which the damage stability requirements of SOLAS chapter 2.1 apply, the degree of subdivision to be provided shall be determined by what is called as, now there is no maximum floodable length, no permissible floodable length. It will be calculated or determined by something called as required subdivision index, represented by capital R. Now, this required subdivision index is calculated in accordance with regulation 6. The formula for calculating R are the function of two things: length of the ship and nature of service. Length of the ship does not need any explanation. Nature of service means whether the ship is a cargo ship or a passenger ship. Nature of service means that. Why? Because you have different formulae for passenger ships to calculate R and different formulae for cargo ships to calculate R, and ship's length will come in the formula. Now you can remember one of these as an example to give this. For example, cargo ships greater than 100 meters in length. Required subdivision index will be calculated by this formula, where LS is the subdivision length of the vessel. So nature of the service, it's cargo ships. Length, A, it's applicable for ships greater than 100 meters. And secondly, length comes in the formula also. If the ship is between 100 and 80 meters, then the formula changes. You don't have to remember all the formulae. For passenger ships, there is altogether a different concept. For passenger ships, it will depend on number of people on board, and you will have different formulae depending on number of people on board to calculate R. So guys, what does this slide show? You don't have to remember all this. What will you say here? You will say here, the required subdivision index R, which is calculated in accordance with regulation 6, is based on the formulae which are a function of ship's length and nature of service. And now, for example, you can give this one as an example to justify what you're saying. Other things I don't think you should remember, because otherwise you'll be cluttering your memory and you'll mess it up nicely. Is that clear, beta? Clear?
Yes, sir.
Now, this is the required subdivision index R that you'll calculate, which will the ship must meet. What will you do at your end? You will calculate attained subdivision index A as per regulation 7 of the SOLAS. So for the ship, what will be done? Required subdivision index is calculated, and then attained subdivision index will be calculated. Details of how it will be calculated is as per regulation 7. Now let me first explain it to you here. This attained subdivision index is nothing but a summation of PI into SI, where PI is the probability of a compartment or group of compartments getting damaged, and SI is the probability of surviving the damage. Guys, it can be done for one compartment at a time, 2 compartments, 3 compartments, 4 compartments. The IMO is very clear that probabilistic method cannot be calculated manually. You have to have a software to deal with it, because probability is a complex concept. Okay, so attained subdivision index is calculated. Now, this attained subdivision index, is it calculated only at one draft? Now, I told you that different drafts will have different safety factors. So this attained subdivision index is calculated for 3 different drafts. One is DS. DS is the summer draft, and the attained subdivision index calculated is called as AS. Other, it is calculated for DP, partial draft, that is called as AP. And third, attained subdivision index is calculated for light service draft, and that is called as AL. So you don't calculate it for one draft, you calculate for 3 different drafts. And then using all these 3 by weighted average method, this AS is given 40% weightage. AS is given 40% weightage, AP is given 40% weightage, and AL is given 20% weightage. By giving this, attained subdivision index value is arrived at, which is 0.4 of AS plus 0.4 of AP plus 0.2 of AL. Now, how do you come to a conclusion whether vessel is meeting the requirements or not? As long as this A, which you have calculated above, is greater than or equal to R, the vessel is meeting the requirements of damage stability. Requirements of damaged stability. Guys, but here there is a catch. Is it only A that you compare? What happens if the ship is very good in summer, very good in partial, but very poor in the light condition? So with 0.4 AS, 0.4 AP and 0.2 AL, you have met the requirement, but in light condition, you can be going for a toss. So to ensure this, so this is one requirement. The second requirement is individually AS, AP and AL need to be greater than or will not be less than, so greater than or equal is fine, will not be less than 0.9 R for passenger ships and not less than 0.5 R for cargo ships individually. Is that clear, beta? And of course, A has to be greater than or equal to R. Am I clear? And individually also, they need to be complying with the requirement. For passenger ships, you need greater safety, so they cannot be less than 0.9 R. And for passenger cargo ships, they cannot be each one of them cannot be less than 0.5 R. Have you understood, class? Yes or no? Clear, beta? Guys, have you understood what I'm saying?
Yes, sir.
Okay. And what is this DP then? Okay, DS you know, DL you know, what is DP? DP will be equal to draft light plus 60% of the difference between DS and DL. Okay. Say for example, let us say DS is, let's say 10 meters. Let's say DL is, let's say 4 meters. So what will be DP? DP will be 4 meters plus 60% of the difference. 60% of the 6 meters will be 3.6. So in this case, DP will be 7.6 meters. Am I clear, beta? Yes or no? Correct, guys? Have you understood? Okay.
Yep.
Okay. So whether the ship is meeting the requirements of damage stability under under probabilistic method, it will depend on two things. One, attained subdivision index A shall be not less than R or shall be greater than or equal to R. Both mean the same. And individually, AS, AP, and AL shall not be less than 0.9 R for passenger ships and 0.5 R for cargo ships. And what is A? A is summation of PI SI. Is this clear what I have explained? So will you now be able to write something about probabilistic method, guys? Yes or no?
Yes, sir.
Okay.
Yes, sir.
You can take a screenshot. I'll be clearing it to show you what is there in the slide. Okay. Once I exit, I'll be deleting it. It will not be available to you after that. Okay,
sir, what is criterion service numeral?
That is obsolete, beta. That's obsolete. That does not exist anymore. Criterion, the service numeral was a number you used to arrive at, and which was used to categorize the ship, whether it's a passenger ship or it's a cargo ship, what type of ship that is. Now that is redundant. It has no place now. If today you go to SOLAS and search floodable length, maximum floodable length, service criteria, numeral criteria, you will not find these terms anymore in SOLAS. Understood? Is that clear?
Yes, sir.
Okay. You will not find these. It used to be a number which they used to arrive at, and the value of the number, it was 23 was the number, critical number. On one side was the passenger ship, other side was the cargo ship. It's all redundant. It does not make any sense now. Okay, beta? Okay?
Yes, sir.
Now, whatever I said here will come now. An attained subdivision index A is obtained by summation of partial indices AS, AP, and AL by weighted average method. Okay. Each partial index is a summation of contribution from all damage cases taken into consideration using the formula A is equal to PI into SI. PI is the probability of a compartment or group of compartments getting damaged, and SI is the probability of surviving the damage. As a minimum, the calculation of A shall be carried out at level trim for deepest subdivision draft DS and partial draft DP, and it shall be carried out at the operating trim in the light conditions. Most of it I have already written in hand, and I think it makes sense now. It continues. I'll take you to the next slide. The subdivision of a ship is considered to be sufficient. When do you decide that she has sufficient subdivision? If the attained subdivision index as per regulation 7 is not less than the required subdivision index calculated under regulation 6. In addition, the partial indices are not less than 0.9 R for passenger ships and 0.5 R for cargo ships. What is DS, what is DL, and what is DP? All these three are contained here. I've already explained to you. And that finishes the probabilistic method. So whatever you start with the slide where I wrote in hand, guys, that extra slide I had inserted. Have you taken the screenshot? Yes or no?
Yes, sir, take up.
So basically, for this particular thing, you'll start your stuff from, did I delete it? Shit, man. Okay, I hope you have this slide which was here. You've taken it, right? Okay. So guys, do you want me to repeat any of the parts about deterministic method or probabilistic method? Tell me. I have told you what to write for probabilistic method. Do you want me to comment something about deterministic method? No? Chalo, good. Then I'm closing this slide and I'll just take 2 more minutes just to show you the Bongian curves and then close out the session. Okay. I keep all these written here so that I don't miss out on any topic. That's why they're all sequential here. It's only this slide that I have to show you guys. Nothing else. That's only single slide. Bongian curves, guys. Guys, when you did the SFBM, what were you doing in SFBM? You were using the buoyancy per unit length. For buoyancy per unit length, how will you get? You'll basically multiply the underwater cross-sectional area at that station with 1 meter of length. That will become the underwater volume per meter multiplied by density will give you the buoyancy per unit length. Also for calculating LCB, I'm not saying KB. If you remember your Simpson's rules, for LCB, you were integrating the underwater cross-sectional areas. How do you get the ship's underwater cross-sectional areas? 2 purposes I have already told you. One to get the LCB, other to get the buoyancy per unit per meter for the purpose of stresses. How do we get the underwater cross-sectional area at different points along the length of the ship at different drafts? So Bongian curves provide that. They are drawn to give immersed area. Immersed area means underwater area, guys, of transverse cross-section to any draft which may be used. And why do you need it? To determine the LCB and to determine the buoyancy per unit per meter to get the stresses, to get the SF load curve. Okay, so this is why you need this. And where do you get it from? You get it from what are called as Bongian curves. So what is Bongian curves? Bongian curves are the curves which provide you the underwater cross-sectional area of the ship. You see, guys, you have the scale down below. You have the curves for different stations. These curves are for the point where they start. So like, for example, this curve is for this station. This curve is for this station. Understood, class? Yes or no? Right, guys? Yes. Now, how will you get? On this, you'll plot the draft forward and aft. Suppose the forward draft is so much. Aft draft is so much. You'll join them with a straight line. Now, I want to know at station 7, what is the underwater cross-sectional area? What is the underwater cross-sectional area? This is station 7, this line. Where is the water line cutting the curve for 7 station? It is cutting here. I will measure this distance maybe with a divider or whichever way, and then bring it to the scale and read it whether I need in meters or whatever. I put it here and I'll read off the underwater cross-sectional area. That will be at station 7. I want it at station 3. Station 3, this is here. Where does the water line cut the curve for station 3? It's here. I measure this distance and read off from the scale how much is the underwater cross-sectional area for this draft at station 3. Is the use of Bunyan curves clear, guys? Yes or no? Am I clear?
Yes, sir. Yes.
Okay. So this was just to introduce what Bunyan curves are. I have not seen them being asked, but if it comes ever, you should be able to draw something and explain what are Bunyan curves. Guys, now from my side, whatever little I could support you in this, I have done my part of the job. Now it's your effort which has to ultimately decide the outcome of all this exercise. What I would suggest is please get going, do the theory, the ship construction part, focus on the numericals. One way to do is that I can request Akshay, if Akshay can post one paper a day from past papers randomly, and if you want to solve it, time your questions. No numerical should take you more than 20 to 25 minutes. Guys, if you come across any numerical or any stability related theory question, which you are not comfortable with in the from any past paper, please take a picture of that question and post it on the group. My request is please post your doubts only on the group. The reason being, once it's posted on the group, everybody benefits from it rather than engaging in one-on-one communication. If for some reason, though you have only few days and I've pinned your group, so I'll be able to keep track of it. But if you feel that you've posted something in the group and I have failed to respond, which is unlikely, but if it happens, then you can drop me a one-on-one message saying we have posted a doubt in the group, please reply. And I'll definitely go and do the needful, though that need will not arise in all likelihood. But if it arises, that is the way you can escalate it to me, and I'll definitely then step in and help you. When is your exam for naval architecture, guys?
4 February.
Sorry?
5th.
4 तारीख को था।
So till 5th, I am available to you for all the help that you need. And don't waste your time on a question which is not familiar and you're not comfortable with. You can just pass it on to me to guide you. Even if it's a theory question of stability, I'll try and make the answer and put it back on the group. Is that clear, beta?
Yes, sir.
Okay, so don't worry. We may have done the delivery, may have completed. You have the full support. Don't unnecessarily panic. And now just press the accelerator on your preparations, and whatever support you need, please do that. Reach out to me and hopefully I should be able to help you. Now I am relatively free because I'll have only one class at Shape now for next few days. So I'll be relatively free and I'll be able to attend to all your doubts without any problem. And guys, if there is a need, if there is an exceptional question which needs for us to be connected, then maybe somewhere on